Okay, so this is meant to go through with you the idea of how capacitors combine when they are in either series or parallel. And so we've already looked at the relationship between resistors in series and parallel. And we're going to see some similarities, some differences. Key thing to kind of note though is that resistors and capacitors are fundamentally different. Resistors consume energy and capacitors store energy. So let's start off with capacitors that are in parallel, or sorry, capacitors that are in series. And we've never drawn capacitors in a circuit diagram, so this is what they look like. There's the two parallel lines. They are different than power supply because a power supply has a big line and a little line. So essentially what happens with a capacitor is that charges are going to leave the power supply. So let's say I have, out of the negative side, I've got 4 electrons that are coming out of the power supply. And what happens is they build up on this plate, and when they build up on this plate, the electrons on this plate get repelled, and they go over here. So if I have 4 electrons that get built up on this plate, 4 electrons will get repelled and then go onto this plate. And when that happens, when those 4 electrons move, I'm left with a positive plate here. And then the same thing is going to happen when I get to this plate. When I have 4 electrons here, 4 electrons here are going to repel, go to this plate. And because they have left, I am going to be left with a positive charge here on this plate. And then same electrons are going to leave and then come back. So like technically these electrons came out, and then we will have electrons going back into the power supply and leaving this plate positively charged. So just by the nature of how capacitors are connected in series, they're going to have the same charge just because it's a repulsion. In terms of voltage, though, if we think about a power supply and this being the higher potential side, so if I make this a 12-volt power supply and this is 0 volts, anything that's connected to this line is at that higher potential. It's at that 12-volt potential, whereas anything connected to this line is at that 0-volt potential. So this plate has to be at a 12-volt potential, and then this plate has to be at a 0-volt potential. So somewhere along the line, I am losing voltage, or voltage is being stored in my different capacitors. So in terms of relationships, we can see that the voltage is going to be split up amongst the resistors, and the charge is going to be equal. So let's kind of just write that down. So this is relationship between charge and voltage for capacitors in series, is that the charge is the same for capacitors in series. Whereas if capacitors are in series with the power supply, then the voltage will get split up. Split up amongst them. So in terms of what that looks like in an equation is that the total charge is equal to Q1, it's the same as Q2, equal to Q3, etc. Whereas the voltage is going to get split up. So my total voltage is going to be V1 plus V2 plus V3. So that relationship is the same as we saw with series, in that the charge is going to be the same and the voltage is going to split up. Let's look at how that relationship is affected in terms of the total capacitance. So we know that the relationship for capacitors and voltage is that Q is equal to CV. And if I rearrange that to say that V is equal to Q over C, then I can use this relationship in my voltage equation down here. So that's what I'm going to do. Instead of writing V total, I am going to write Q total over C total. So this would be Q total over C total. Instead of writing voltage 1, I am going to put Q1 over voltage 1. No, I am not. I'm going to put Q1 over C1. And then Q2 over C2, and then Q3 over C3. but I know that for capacitors in parallel, no, I know that for capacitors in series, the charge is the same. So all of these Q values are the same. So my relationship ends up becoming that capacitors in series add up as inverses. So that is opposite as to what we saw with resistors. So the relationships are the same in terms of charge and voltage, but how the total capacitance adds up is opposite. So we would expect that for capacitors in parallel, they should just add up. And so now we're going to shift and look at how capacitors in parallel are related to each other.